I'm very happy to share my experience of debugging KVM using Intel DCI technology. This is my first time to present in KVM forum. I will do a quick self-introduction. My name is Raymond Zhang. I used to work at Intel from 2003 to 2016. In 2009, I joined a project which is based on Xen. Our goal is made NVIDIA graphic GPU to work in Windows VM. At that time, it's quite difficult to make a graphic GPU to work in VM. Usually, there is a very weak GPU inside VM. After we passed through the device to VM, we installed the driver, its binary, and there will be there was a random TDR blue screen. I spent significant effort to do the debugging. After 3 months, I found the root cause. It's a bug in the MMIO code of the shadow memory logic of them. At that time, the only way to do debugging is print and log. So today, I will share how to use a debugger to do the debug, which is much more efficient. Here is a classic Xen architecture. There is a hypervisor under all VMs, and there is a special VM. It's called domain 0. It's a privilege. It provides service, and it also manages all other VMs. For example, there is an IO process for each VM to do a device emulation. And usually, we only let domain 0 to see the real hardware. All other VMs only see the emulated fake devices. The Hyper-V from Microsoft has a similar architecture. There is also a hypervisor under all VMs. In Microsoft's term, VM is called partition. The parent partition is equivalent to domain 0 of them. And for Windows 10, Microsoft introduced a feature called isolated user mode. Also, it's called virtualization-based security. If this feature is enabled, a Hyper-V hypervisor will run. And above that, Windows 10 is running, and there is also another special secure kernel run on top of the hypervisor. There will be a lot of VM exists when Windows access hardware. So after this feature is turned on, actually the performance will be sacrificed. I think KVM has a different architecture and is better. So I believe KVM has a smarter design. From the architectural perspective, KVM combines domain zero's kernel and hypervisor into one. Actually, they are run in one address space. With this structure, it has a lot of benefits. Domain zero's kernel will not exist to hypervisor when it accesses hardware. So it has advantages, a lot of advantages. Some people may not agree with my previous diagram. So here I will show some code. Here is a code from vmx.c. Actually, is code from Intel to support VM technology. We can see is VM extension for KVM. So this function has very important operation, that's VMX-on. VMX-on is an instruction from the CPU. Actually, it turns on the hardware support about VM, about VT. Using this example feature of debugger, we can see the instruction is inland into the hardware enable function of KVM Intel module. The VMX-on instruction has very special role in the VM in the VT technology. Actually, the software which execute VMX-on firstly will win the hypervisor role, or other after that, if other software executes the instruction, it will fail and it will be treated a traitor. So with this diagram, actually it shows CPU's execution route in a VT environment. We will talk it later in more detail. We can set a breakpoint at the VMX-on instruction. After we set the breakpoint, we let the target go, and we launch KVM VM in the Ubuntu target, for example. After we click the launch button, the breakpoint will be hit. And using the call stack function, we can see the call stack. From the call stack, we can see the Linux kernel is invoking KVM module to do hardware enable. Actually, it's using the Linux kernel's SMP mechanism to let all CPU ascend to VM to enable to turn on the feature. After KVM gains the control, it will invoke KVM Intel. Actually, is a function pointer registered into KVM. So we can see the hardware enable function execution, and it will execute the VMX-on instruction. after this instruction, actually, the code which executes the instruction with the hypervisor role. And according to this code stack, we can see the hypervisor code and the Linux kernel runs in one address space. So it's safe to say the hypervisor and the Linux kernel is run is combined in KVM architecture. Actually, the KVM name is very good. It means kernel-based virtual machine technology. So the kernel plays the hypervisor role. Is smart. Just a quick view of KVM. So nextly, I will talk about DCI. Then I will talk how to debug KVM using DCI. Here is my debugging environment. Actually, I'm in travel and I'm talking in a small hotel. Here is the machines I used. So laptop is running as host, and for the target, I run Ubuntu. I turn on the KVM feature and also installed Ubuntu inside one VM. The hardware of the target is Intel CPU, low power. For the target, the BIOS is customized. I will talk the reason shortly. Between the target and the host, I use a USB 3 cable to connect them. That's the DCI technology. So DCI stands for Direct Connect Interface. The name is very easy to understand. It means we can connect the host with target very easy, very direct. I think before DCI, we have to open the traces to connect the ITP connector. Before DCI, Intel used ITP technology to do low-level debugging. For ITP way, the connector is on motherboard. It's not opposed to traces. So we have to open traces. That's inconvenient. So for DCI, actually, it's introduced by Skylake in 2016. I believe it's a very very good technology. It holds the powerful ITP, that's JTAG scan twin technology to USB connector, which is very easy to do connection. Inside the silicon, actually, there is a new component called XDCI. XDCI will work with JTAG scan twin and transfer the data to XHCI. That's a USB 3 controller. They will work together to expose the ITP technology to a convenient USB port. Here is the device list using DCI debugger. Actually, here is an Intel System Studio. I think the beauty of DCI debugger is you can see a lot of internal devices using the debugger. For example, here we can see the internal core, also the on-core part, also the integrated devices inside the chip side. So for people doing low-level development, for example, OS development or Java development, I believe it's very useful. Actually, there are two types of DCI. One is called boundary scan sideband hosted DCI. It needs a small box. The box is called closed traces adapter, CCA in short. The other way is called USB hosted DCI. It only needs a USB 3 cable. The second way is low cost and is convenient. Actually, I'm using the second way. The constraint of the second way is it can only do I0 debugging. It cannot debug early wake up. For CCA, it can debug early wake up. That's the advantage of the CCA tool. I have to mention that to do DCI debugging, we need usually a customized BIOS. The reason is for security concern. Intel advise our OEM to turn off the feature in BIOS. That's lock the feature. After it's locked, it cannot be turned on again without power cycle. It means if it's turned off inside BIOS, there is no way to turn on it in OS. That's why we usually need a customized firmware. Sorry. After introduce the DCI, then I will share my experience about debug KVM using DCI. I will talk some typical scenario to do the debugging. For example, debug VM create. There are a lot of steps to create a VM. I will talk some examples. For example, here is a breakpoint on VMX create vCPU. When this breakpoint hits, we can examine the details about creating vCPU. After creating vCPU, the KVM will create virtual MMU. Virtual MMU, I think is just a simple name. Actually, it's creating the facility of memory pages for the VM. That's turn on the, for example, the EPP technology of the hardware. If no EPT support in hardware, I believe it needs a special shadow page mechanism in software. After creating a vCPU and the virtual MMIO, the KVM will create local APIC for the VM. Local APIC it means advanced programmable interrupt controller. That's virtual PIC for the VM to do interrupt transfer to the VM. After that, KVM will also create some facility to emulate Hypervisor VM bus facility. I believe this is to speed up the device communication between VMs. In the times, I think in the 10 years before, we usually emulate the device using the real protocol, but it might be slow. The VM bus has a special protocol defined for VM. It has better performance. After that, KVM will create a programmable PIT for VM. It's for timer interrupt. Timer interrupt is a classic facility for PC. Actually, today is still used so that the machine has clock support. So after so that's about VM create. So now I will talk VM exit. Actually, after a VM is created, CPU will run the VM launch instruction or VM enter. Then the CPU will enter the guest domain and run the instruction inside the VM. For normal instruction, there's unprivileged instruction. The CPU will directly execute the instruction. That's called direct execute. But when CPU meet privileged instruction or IO instruction, then it will exit. That's called VM exit. So from to some extent, when a CPU is running a VM, it runs in such a loop. Enters VM, and if it meets a special instruction, it's also called sensitive instruction, it will exit to hypervisor. Hypervisor will solve the issue, and after that, it will let the CPU enter the VM again. That's the loop. So here, VM exit doesn't mean VM shut down. It means VM CPU exit from VM for some reason. One typical reason about I/O access. I think this is also the primary way to stop VM destroy hardware. In a VM environment, there are several VMs. They may share one real device. So if they access hardware, it will exit, and the hypervisor will do the management. Here is a breakpoint and in the debugger, we can see the code stack and source code. Actually, there are two types I/O. It's called the first is port I/O. Is old and it's inefficient. It's created by the classic PC ports. Right now, most I/O is memory mapped I/O is more common and better performance. So for hypervisor, actually today we use QEMU in both KVM for both KVM and Xen. For QEMU, actually it will register I/O port function callbacks for I/O port. So actually, when we create a new virtual device, the main job is to do to develop the read-write callback. And in KVM, there is a KVM I/O bus. It will management the all I/O ports and the register function callbacks. For example, here is a VM exit for port I/O. Then at here it means CPU do the I/O access inside VM and exit. After exit, KVM will invoke, will handle the exit and invoke KVM Intel. That's extension by Intel. And KVM Intel will will check the exit region and invoke the fast PIO function. Also, then it will walk through the I/O bus to find the read-write callback and invoke the callback. Here we can see the port address is 71. Actually, is the classic CMOS device. Here is a abbreviated call set. Then I will talk another example about memory mapped I/O. Here, actually, the APIC is using MMIO. It's read callback, and here is call stack is in debugger. We can see it's a write access and invoke the KVM write MMIO, and it will dispatch to the APIC function register callback. From the parameters, we can see this is a special address. Actually, it's the APIC register. In the APIC spec, it defines the linear address range beneath 4 gigabytes. Actually, is reserved for APIC. So here are some useful breakpoints to debug KVM for reference. Here is a quick real case. Actually, when I turn off the target machine, they want to take a long time at the power off screen. It seems hung on somewhere. Without a debugger, it's very hard to do the debug. Then I use the debugger to break it. Then the target breaks into the debugger. I check the CPU 0 firstly. From the call spec, it's servicing a reboot interrupt. And from the source code of the reboot interrupt, it's doing stop CPU. Actually, this function will trigger the, I believe it will trigger API to let all other CPU respond the command. And when we switch to CPU 2, we can see it might panic. and it's in constant delay. So that's why the hang. It means when we turn off Ubuntu with some VM is on, there are some special calls triggered panic of Linux kernel. With this panic, there is delay inside the kernel and cause I believe is about 1 minute delay. So that's all about my talk. I'm very thankful for your attendance, and see you next time.